right, so there's actually two pretty good versions of starting processes here. So if you say mole ratios first, Levi, tell me what your process is. So mole ratio of H2 is what? Say again? You have a calculator, right? Could you possibly do that for me? So 0.5 moles divided by 1.75 moles. Say again? 0.29. Okay, I'm going with the flow here. And you say if you did that one as a mole ratio, then you're doing another one as a mole ratio. So that's 1.25 moles of helium over 1.75 moles total, which is so just the difference, and that's a good point. So as you're looking at mole ratios are just basically a version of percent. Percents, of course, always add up to 100, but mole ratios always add up to total of 1, right? So if you got 0.29, you could have easily gotten 0.71 without implementing this ratio, just by subtracting from 1. You got me? All right, so that's an easy step. So how are you going to use this to find the partial pressure? I'll let Levi continue your thought there.
That's something moles you put into your ideal gas law equation.
Okay, so this is what's the total pressure when the gases are mixed in a 5-liter container, right? So if this is the case, you say volume for this total container over here, volume is 5 liters. What would be the other variables you know for the ideal gas law?
Your moles is 1.75.
Okay, so now we're doing total moles, but we just did separate. So we're going to use this stuff later or now?
No, you'll split it up later after you get your total.
Okay, so we'll use this later. Good point. So right here, that's probably like, oh, your first instinct may not be what you start with, but it's going to be implemented later. So make sure you hold on to that. Don't erase it all because you guys are like, oh, no, it's wrong. You erase it. Don't erase your work. It's probably okay. Okay, so we're going to find total. So you say find total pressure?
What? Yeah, you find the total pressure.
So that's our question. Okay. What else? What other variables do we know? Oh, you said total moles was 1.75. So how did you get 293? So 20 plus 273 is 293 Kelvin, and then you're good. So why are we allowed to implement the moles as a net moles? Won't they cause different pressure? Why? Why is the average kinetic energy the same for all the particles? They're at the same. Say again? No, hydrogen gas and helium gas are not the same. Kinetic energy. They're at the same temperature. Temperature is related to average kinetic energy. So temperature in Kelvin is related to average kinetic energy. So we are making this assumption because we know the relationship. Okay, and that's good. And if they ever asked you, justify why you're able to do this mathematics in this manner, then you'd be using something like that as your justification. So they like to ask a lot of word explanations on things like this. So PV equals nRT, P is equal to nRT over V, N is 1.75 moles, R is 0.0821 atmospheres, liters per mole. Okay, and temperature is 293 Kelvin, and volume is 5 liters. Don't calculate this yet. Let's see if we can estimate. Here's how you estimate with the ideal gas law. Because you will have multiple choice where you have to estimate using the ideal gas law with no calculator, right? So work with me here with no calculator. You guys with me? Thank you. Thank you, another way. So if you have 293 times 0.08. Well, 0.08 is approximately what percent? 8%. Well, that's about 10%, right? 8% is about 10%. This is our mental math madness, okay? That's about 10%. What's about 10% of 293? 29.3. You bounce the decimal back one. Okay, so in your head, you're going 1.75 times 0.1 times 293. All right, so 29.3 is what this is together. So 29.3 times about, let's say if I multiply by 2, what would it be? So that's about 30, right? So 30 times 2 is 60, but it's got to be about a quarter less than that. So hold off for a second then. Let's keep this about 60. We know it's going to be less than 60. 60 divided by 5. 12. You know it's going to be less than 12 though because that's less than 60. So if you're choosing multiple choice and they were 1, 2, 10, and 15, what would be the best? 1, 2, 10, and 15. 10. A lot of times multiple choice answers are decently spread out that you could do an estimation. And of course we overestimated because we said 2 times 30 versus 1.75 times 30. Right? 2 times 30 is 60. 60 divided by 5 was 12. But we know that's an overestimation. So then from a multiple choice perspective, they would be totally spread apart enough that you could actually estimate and go, it's got to be the one that's a little less than 12, but not too low, but not too high, right? So that's why I just made up that you said 10 would be the best. Now actually calculate it. Truly calculate now. So just trying to help you out with those mental math skills that you so desire. Anybody got the calculation yet?
8.42.
Say again? 8.42, so we are way overestimated. Atmospheres, right? So P total is equal to 8.42. Anybody else?
Yeah.
That's good? Okay. I like to have a good double confirmation. So now I have the total pressure. That's the first part. Then how do I get the partial pressures? By the total, right. So take my mole ratio, P of hydrogen is equal to 842 atmospheres multiplied by what was that, 0.21 or 29? 0.29. Okay, that's our partial pressure of hydrogen, and then partial pressure of helium. Same story, 8.42 atmospheres times 0.71 as our mole ratio. What do you get for each of your partial pressures?
2.41 atmospheres.
First one, 2.41.
Yeah.
Okay, second one, 6.01. You could do that either by simply calculating across or by doing what? Right, you could do P total minus P of hydrogen to equal P of helium. So you could do that as well. So you're seeing all these relationships, vertical relationships, horizontal relationships. We see that there's a lot of things interconnected, right? Did everybody make sense of that question? Shake your heads or something. Okay, so I'm going to leave it there for a minute. So we didn't get to do this yesterday. I know some of us have actually done the crush the can lab, but it's a 5-minute ordeal. I think that it makes sense to talk about this with pressure. So I'm going to do the instructions on the board. After that, I'm going to do my pumpkin demo, which Jackie was supposed to help me with, but he's not here. So we're going to do that, but I'm going to scroll back to the instructions for crush the can. Then we're going to do a kind of a group elaboration on what all of that means before we start gas law stoichiometry. So does anybody know how to start crush the can?
No, you get all the materials.
Step 1, get the materials. Okay, let me pull this down. All right. What you do is you're going to get a hot plate. Hot plates already have beakers on them. The beakers you need to make a ice bath full of water and ice in your beakers. That's going to be your cold bath. You're going to heat up your can on the hot plate. It's going to have just a teeny amount of water in the bottom. That teeny amount of water, once it starts heating, is going to create gas. It's going to evaporate. Then you're going to take your beaker tongs, grab them, and immediately flip it over in the ice water. Don't look how pretty it is. Wait. No. Quick. Jump into the cold water with the whole of the can down. All right. Get started. I have five set up. You guys can break into 5 groups. Somebody take Arushi. She's all by herself. The ice are in the 2 coolers right back here. You guys have 5 minutes. Get that can started. Get the can started. Step one. Get the hot plate heating up with the pan on. The pan has to have what? A teeny amount of water, like 1 milliliter. Teeny amount. And that's going to take a lot of water, okay? Use that. So that makes the ice. Actually, because of the sauce, it's so much fun. Three to 4 minutes. There's a whole nother cooler of ice over here. You want it? Alright, so, just talk about your gas laws or what you're going to bring for mold day or, style compounds. You didn't wait long enough. Whatever. And don't do it soon. Don't just wait. If you want to wait for me, I can give you the. Okay, go ahead. No one's ready yet. You'll hear it start to pop. You'll see some steam, but wait till you have a lot of gas. Well, you know what? You don't have to sit base it. Come back up here for a second. Come back up here.
Yeah, we can go.
I need to get a beaker of water real fast. Sorry. Beaker of water that I don't have right now. Alright, it's okay. These will steam for a moment. It's coolio. Come gather. Come gather. Let me get my goggles on. What's about to happen? It's about to go down, guys. It's about to go down. It's about to happen. Leave your stuff going. This is for the Snapchat with your goggles on and my goggles on, and quality instruction here. So, what we have here is me still trying to speak in tongues here. So I'm going to make acetylene gas. Acetylene gas is flammable, and my goal is old pumpkin. Doesn't mind. So, gotta wait for the gas to form. Now, if his pieces come out, I need his pieces back. I will tell you when. No snaps yet. Just wait. We have to let this create a good, happy environment on the inside. Alright, I think that's probably good. So, 1, 2, 3. Hold on. There's pumpkin in my Okay. This is gonna be bad. Okay. So, alright, I need his little pieces back. I hope that I got. Oh, and his eyes didn't come out. Okay, we're gonna do this again later. We'll do it again. Just gonna keep trial running this all day today. Go do your hands now. Ice cream.
Want to be sure or not?
Alright, I want to hear the can. I want to hear it.
We good?
Let's go.
I was super quiet.
Let's go.
Oh, you're not one. Oh.
Let's go. And turn your hot plate off. Turn your hot plate off. There you go. Are you going to use some?
I can't go any further.
Very good, Jack. Alright, and turn off your hot plate and back to your seat. Throw the cans in the recycle. Into your clean green vacuum machines. Let's go. Thanks, Jack.
I think I left my text on to you yesterday.
Yes, here.
Oh, it's pretty good.
Okay, so you want to take your
that?
take your redox?
Can I not pick the box today?
Oh, I got it here.
Oh, yeah.
But I can put you in the teacher.
Okay, sweet. Because,
We'll make it work.
sweet.
Don't worry about it. Alright, kids. I only call you kids because you're younger than me. It's okay. We'll clean up the ice. Okay, pour the ice down the drain. We'll go. Alright, you have 1 minute to craft an explanation of what happened. Don't say it out loud yet. And I'll have to do this again for old Jackie. Oh, huh? It is hot out right now. But it popped out this morning. I said it in. I shaved them all down so they could find out their leaves. But I did it this morning for teachers, and then it worked really well. And then this thing got clogged with pumpkin poo, so. Alright, you have 1 minute, less than a minute. Actually, go ahead now. Go ahead, you bad selves. Anybody got an explanation of what happened? Kirk.
We slowly increased the temperature, and then we lowered it really quickly, and the volume had to decrease.
So the volume had to decrease. That is a true statement, but that is not what the cause is. Just like I say apples are red. Is that me explaining this question? No, right? Like, it's what you guys do. You like to say the right answer, but it's not the right answer. You know what I mean? Yeah.
Okay, so it gets hotter, and that increases the pressure, like
Inside the can.
inside the can because of the collisions.
Okay.
And then when you put it in, the outside pressure isn't equal to the inside.
Well, if it's when you put it in, what happened? Why didn't it explode or implode before you put it in?
Because it was.
It's related to what Kirk's saying, but he didn't complete his thought. It is related. So you start heating it up, right? It starts speeding up. They start colliding more. The pressure increases, right? It doesn't increase so much that it explodes, but it increases a lot. So the pressure on the outside and the pressure on the inside of the can are fairly comparable. But then you flip it, and what happens?
The pressure inside the can is a lot less than pressure.
Oh, why is it less?
Because the particles inside the can are really moving that much.
Why?
Because it's colder.
Because it's cold. Okay, so that's wrapping in Kurt's explanation with the Rishi. So because you've chilled it, and normally if you start to chill something, the gas particles start moving slower, they start causing less pressure. The atmospheric pressure on the outside is like, oh, let me throw some more gas in there, we'll equilibrate this pressure, we're going to be fine. But why could it not do that? It was submerged, it couldn't allow for equilibrium to occur. So, no more equilibrium, it has no place else to go but in, because the pressure on the outside crushed it. Okay, and I forgot my egg. I was at a professional development till like 9:30 last night with college, so I was going to boil an egg and cheese for the egg demo, but I'll do that next week. Okay? All right, so you guys know how that works. Let's talk about pressure a little bit more. I did skip one thing yesterday for pressure, and we're going to do stoichiometry. Stoichiometry! Okay, here. So this is the part I did not do yesterday. We're going to write down a couple notes with this and implement that into our stoichiometry questions. So we're going to do stoichiometry for about 20 minutes, and then we're going to practice. And I'll have to do the pumpkin demo one more time. So are you guys writing through or not writing through? Like, how do you guys take notes? What's best for you? This is not in the packet.
You can record your voice.
I'm recording, but I'm videoing, but I don't know. I highly doubt some of you guys go back and watch the video, so I prefer you to write something down so that you have some real backup. And I'm fine to start explaining, but I want to give you a chance to explain with me. So this is pretty much Dalton's law, talking about how if we have an experiment, and a lot of times your lab-based questions will be implemented in your multiple choice or in your free response. If you have a water column that's in the UDometer tube, that's what I drew yesterday, was that big upside-down tube. You guys will be using one of those next week. And we have to collect gas, which I think Levi said yesterday we collect underwater. Collecting gas underwater is our only way to capture gas in a confined system, because we allow it to bubble through the water and then be captured. But with that comes water vapor. So we have to always recognize water vapor is there, and if water vapor is there, we have to subtract it from total pressure to just simply isolate gas pressure. Because the gas of interest is what we are talking about when we talk about an ideal gas law situation. So the ideal gas law, when we say P, we're talking about P of that gas. Unless it's talking about a total situation like we did for warm-up today, we have to isolate just that gas. So P of gas is equal to P total minus P water vapor. And P water vapor is always going to be specified at a specific temperature. And that temperature, you don't have to memorize, 20 degrees Celsius water vapor is blah. 21 degrees Celsius water vapor is blah. I have a humongous reference book that has all these values. Online has all these values. And usually in a question, unless I'm negligent, usually in the question I'll put P water vapor at 20 degrees Celsius is blah, because that's always a reference point that you will be given. And then we have the water column, because sometimes if we have that little beaker situation where we have our water, and we put water, I'm going to color water green today, and we put our water in this tube, and it's all the way up the top, and then we start collecting gas. Well, the gas is starting to displace the water, right? And so as the gas displaces the water gets pushed down. And so let's call this red up here gas bubbles now. Okay? Well, let's say that's the extent of the gas we collected. Well, we're stopping here, which is a problem, because if the water on the outside of the UDometer tube and the water on the inside of the UDometer tube are not equal, that height difference actually causes a little bit of a pressure difference. That height difference we call the water column, because it's a column of water. Our goal, and which would be way easier if we could just do this, if we could always get the water column equal to the outside water level, we'd never have to deal with this. But that's, sometimes it's going to happen, sometimes not. So I want you to be comfortable dealing with both situations. If the water level on the outside and on the inside of the UDometer tube are equal, we assume P total is equal to P of atmosphere. That's the assumption. But that's not the case because we have a water column here to deal with. So the water column is going to be a specific height in millimeters. But millimeters of what? What are we measuring? We're actually measuring water, right? Is millimeters of water a pressure unit? No, but millimeters of mercury is a pressure unit. So there's a conversion between the two. The conversion is utilizing density and height. Density and height together will give us our ability to compare water to mercury. So that's what this right here is. So the way you find it is you set up height, this is really small for you guys in the back, but height of mercury times density of mercury is equal to height of water times density of water. And so density of water we usually just go ahead and assume is what? Sam? 1 what? Okay, gram per cubic centimeter or gram per milliliter, interchangeable, right? So if we assume the density of water is 1 gram per milliliter, what's the only unknown variable here? It should be the height of mercury. Because actually the density of mercury is a standard value as well. The mercury is really, really dense. If you've ever felt a mercury thermometer, like with true mercury in it, it's very heavy. The mercury's density is 13.6 grams per milliliter. So to solve for height of mercury in millimeters of mercury, all you would do is take the height of water, which would be in millimeters, of course, because you got to compare apples to apples. That's just you taking a ruler and measuring the height of water, and you would divide it by the density of water times the density, divided by the density of mercury, because the density of water is 1, it doesn't affect our measurements. So once we get this height of mercury, this is the P of the water column. Thumbs up if that process, the reasoning behind it, and why the heck we're doing this makes sense. Give me a question. Yeah.
So with the water column, so when you added and when you subtracted, like what if like the water level is below?
Is
above?
if the water level is, so within the column, if the water level is above, it's causing pressure. It's an addition, so it's a part of the total pressure. And that's why we're subtracting it up here. Because the total pressure, subtract the little bit of water that's just vaporized in there, plus, or also subtracting the water column. If we take away both of these from the total pressure, that's going to give us our isolated gas. But if the water column is, you're right, if it's below the water level, we have more gas, so then it would need to be added back to the total. Is that what you're asking? Yeah. It would be just opposite because it's actually more, there's more gas pressure, so the pressure of the gas would need to be a higher number. Yeah. Hopefully we never do that in beach dubs. Try never go to below. Because a lot of times we just stop making gas, which is why the water column exists, because we literally can't make any more gas. If you have the power to stop making gas, you should stop, because you can always, it's okay if you're not making all the gas, you can always stoichiometrically calculate backwards. Yeah.
So the gas you're testing for is at the top of that column.
Right, and it's probably like hydrogen gas or carbon dioxide, something that we make from a decomposition reaction. All right, we okay? We'll implement this in a question here. Okay. Other point to make is just make sure if we are dealing with millimeters of mercury for one of them, we got to be doing it for all of them. So just make sure that you're writing your units, so we all are speaking the same language. All right. So we're going to use this in a stoichiometry example. Well, this will be before the stoichiometry example. Let's go ahead and do this one first. So sample of oxygen is collected over water. That's basically me saying u diameter tube at 20 degrees Celsius. So temperature 20 degrees Celsius at a pressure of 738 millimeters of mercury. The vapor pressure of water at this temperature is 17.5 millimeters of mercury, and that's what I was saying was in a data table, like in a big book or online. I am telling you right now, P of water vapor is 17.5 millimeters of mercury. And it's always going to be a pretty small, insignificant amount, which is why it's 17. It's pretty small. What's the partial pressure of oxygen? So when I ask for partial pressure of oxygen, you're asking for PO2. So this P that they give me first would be P what? P total. So identifying what's your P pressure total, your pressure of water vapor, your pressure of your oxygen gas, which is your gas of interest, that allows you to see what formula you have to implement. Does it say anything about a water column? No. So this one's easier than that setup we just showed. How would you find the partial pressure of oxygen? simply subtract, right? You'd be P total minus P water vapor equals P of oxygen. And that's it. Now, if it did say, oh, I had a 70 millimeters of water height of water column, you would then also convert that to millimeters of mercury and then subtract that as well. These are not hard problems. These are like, whose law is this, by the way? Dalton's law, right? Now, we assume if they're at the same temperature, the gas particles cause equivalent pressures according to their number of amounts they have. So when it says, what's the pressure, what's the volume when it's dry? When it says dry, it means you have subtracted the appropriate amount of water vapor. And so this pressure of oxygen we get here, how would I then find its volume? After I get this is dry oxygen. I have P, I have T, and it's asking for V. What would you need here? You would need moles to find the volume. Because you're not giving enough information. Oh no, sorry, I lied to you. This is the volume right here. I neglected to write that down. V total, 310 milliliters, that's V total. So then you could find moles the first time, right? Using P for your P of oxygen, your T for in Kelvin, of course, and this volume would be, you could actually take your volume total and you could subtract your volume of water vapor, which you found its actual volume too. You could do this in probably 2 or 3 ways actually, depending on which order of operations you did. But I want to do one with, I wonder what stoichiometry involved, because I thought this was my example of oxygen, but it's not. I'll come back to this in a second. I just want to demonstrate this process. So, gas stoichiometry. What does that generally mean we need to employ? Okay. Gas stoichiometry. Say again?
Can you say the gas law?
Okay, maybe the ideal gas law, but what's it going to be in reference to? 22.4 liters per mole would be like an STP. That's converting between moles and liters. When you're doing stoichiometry, a lot of times you're going to be doing reaction stoichiometry, right? So reaction stoichiometry requires a reaction and information about the gases just enough so that you can calculate a true moles or volumes given the circumstances. So I'm going to go a little forward, and I want to do actually an example with you guys first before we start going over questions. Well, okay. We're going to start with this question here. Because I think a lot of this is background information in terms of, I know how to do reactions, I know how to do stoichiometry, and I know how to do gases, it's just we're compiling them together here. So in this example, it takes potassium chlorate, and you're going to be decomposing it. So write down your decomposition reaction of potassium chlorate first. It requires some, like, 2 weeks ago decomposition reactions that you knew. What do chlorates always decompose to? Chlorates. Anybody? Say again? Oxygen gas and say again? It's actually, so what you should memorize is metal chlorates always decompose to metal chlorides and oxygen. You just memorize that. I'm not going to give it to you. Okay, and especially if on a gas law question where you have to find something at the end, it's really hard if you can't get started. So in this case, metal chlorate is potassium chlorate, yields, and the triangle over the top means heated, right? Okay, yields what? Potassium chloride and oxygen. Balance? Balance for me.
2, 2, 3.
Thank you. Okay, yields acetylene gas. All right, so sample of solid potassium chlorate was heated in test tube, and we will. Start right now, you're good. Someone. Hey. Yeah? No. so we will do a lab like this later this unit. All right, so oxygen was produced, and oxygen was produced by water displacement at a temperature of 22 degrees Celsius, which is useless, right? So 295 Kelvin, okay. The volume of gas, and so this is where I think it's very important for you to write down what gas. Volume of what? O2. Volume of oxygen collected was 0.650 liters. The water vapor pressure, P water vapor, is 21 torr. Okay, so you're going to look at and see where your torr conversions are momentarily. Calculate the partial pressure of oxygen, question 1. And then second, the mass of potassium chlorate that was decomposed. Mass of KCl3. Okay, so what do we not, or what formula do we have enough information to employ? Anybody? Okay, so we'll find our partial pressure first by taking, do we have P total? Say again? Did I not write that down? My bad, thank you. I was like, I'm missing P total. So P total, 754 torr. Right, so I'm going to go ahead and do P total minus what? P water vapor. Okay, that's going to be P gas, that's going to be P of oxygen. So 754 torr, subtract, thank you, 21 torr, gives us 733. So you said, I did it in a different way, but 733 torr. Okay. So, does anybody know the conversion? And I'm just going to go ahead and say, you know, assuming we're going to do the ideal gas law to get something about amount, meaning moles, I can't use torr in the ideal gas law, right? So what do I need to convert to? Atmospheres. What's the conversion with atmospheres and torr? Yes, it's the same as millimeters of mercury. It's 760. So I don't think we wrote that down, but it's in your reading guide. So 1 atmosphere, I'm just going to go ahead and convert since I know I need to. P of oxygen, 733 atmospheres, 760 torr, gives me what? Have your calculators out for us here.
0.97.
Point. Um, 952. Got anything more specific?
96.
Honestly, I converted atmospheres first and then I subtracted them. I got 0.952. Can anybody else just double check that? Can you take 733 divided by 760 one more time?
Yeah.
0.6 what? 964. That is perfect. Okay, atmospheres. Okay, so if that's our partial pressure of oxygen, what would you want to find next? Assuming we've dealt with this and this so far. So how are you going to find moles? Ideal gas law. So P equals nRT. N is equal to, give me the rearranged variables here. So, say again? PV over RT, right? So you're dividing by the RT. So P of oxygen was according to you guys, 0.964 atmospheres. V of oxygen was what? It was written right there. What was it? 650. So 650 milliliters needs to be converted to liters, right? 0.65 liters. And then R, 0.0821 atmosphere liters per mole K. And temperatures what was it? 295, thank you. All right, how many moles is that? Okay. Say again? 0.02, can I get some more decimals? 58. 0.0258 moles of what? Okay, this is super, super important. Do not forget this is a gas. Okay, this is O2 gas. This gas, I mean, because we're doing an ideal gas law, you can't plug solids into gas laws. Absolutely not. So you were talking about the gas here. So when you go forward and you're like, oh, the question says figure out potassium chlorate. I mean, now what's the mass of it that was decomposed? A lot of people will go, oh, I have moles of potassium chlorate, and then they'll just convert straight to mass. That's the biggest mistake people make on questions with stoichiometry. So assuming this is oxygen gas, because it is, 0.0258 moles of oxygen, what would I do with this now so I can move forward? Okay, so how do I convert to moles of the solid? So look at the original reaction and see it's a 2-to-3 ratio, right? That's where the stoichiometry mole ratio BCE comes in. And what was that? 2 moles of KClO3, 3 moles of oxygen. And then do I have to stop here and get moles? No, what's the question asking for? Mass, right. 1 mole of KClO3 weighs 122.55. So please calculate, double check that. 122.55 grams. And that gives me my final answer, hopefully of 2.116 grams, which should be rounded to what for sig figs? I think it was 3. Let's double check all our data. Was it 22 point? So using Kelvin, 3 sig figs, the pressure should be 3 sig figs. So 3 sig figs is what so 2.12 should be our final answer. Okay. So that's reactions, stoichiometry, and gas laws all together. The truly hard part is just making sure you know what your quantity is talking about, so you can make sure you're moving in the right direction. So I'm going to have you guys do a couple more of those, but I'm going to have you do them from your problem set. You guys did 1 through 6 yesterday. And now that we have kind of this one more part under our belt, you should be able to do the rest of them. 7 through 11. And I want to see, I think I have one more example on a specific one because I tried to do the hardest, most inclusive ones up on the board. But we have a little less than an hour left. So you guys are actually going to, because we get out at 10:30. I think. Yes, we get out at 10:30. Non-field days are weird. So you guys are going to have plenty of time to finish up some things, okay? And I will, if I need to put textbook questions on the board, I have my textbook and I'll put them up there. So you can probably get a bunch of stuff done. So there's not much to do this weekend. Yeah, work out loud, and then when I call you back, I'm going to do another example for the group. So please make sure you're working for me. Get your problem set done. I do have a couple more, but if you get it, I don't need to keep killing a dead horse. So let me know how you do. Yeah. I'm gonna let you guys work for like 10 minutes, and then I'm gonna do another one because there are a couple more I need to do. Nitrogen into gas. Okay. Now you need all your work to support these. You're just jotting down answers. Make sure you have work to support. 2A. 2.07 atmospheres. Good. B. 17.7 grams of chlorine. Give me thumbs up so far. We're okay. Emma, what's up? Where are we at? For number 2A, what did you guys get for your pressure? Okay, good. And you took your moles to chlorine gas by using diatomic chlorine, which weighs 70 grams per mole. Okay, cool. Density for 2C, 5.908 grams per liter, or 5.91 grams 66 grams per liter for gas. 3A, 0.82 moles. That was simply a conversion from grams to moles. B, when you plug in PV on RT. Say again?
338.
So that, I think it's specified for Celsius, so 338 Kelvin would be 64.9 degrees Celsius for temperature. That's good. As long as we're close. Yes.
And actually that's for both Kelvin and Celsius.
Okay, that's fine. I guess. All right, 4. What was the pressure? 0.960 or 5. It depends on our specific numbers we put in for molar mass. Atmospheres, and that's using that dirt over P, right? Molar mass is dirt over P can be rearranged just off of P. 5. Say again? I got 1.43 grams per liter. So what there are 2 ways to do this. Somebody tell me, so Lee, tell me how you did it.
I use the RT or the P equation.
Okay, you solve for B.
Solve for D and use 32 milligrams.
Right. Remember, oxygen is diatomic. They use 32 as your molar mass. There is another way to do it, and it's cheap, but it works. Molar mass divided by volume. Add STP. If the molar mass of oxygen is 1 mole, right? 32 grams is 1 mole of oxygen. 1 mole is what volume of STP? 22.4. So you take the 32 grams per mole and divide it by volume of 22.4 liters per mole. Moles and mole cancel. It's grams over liters in the end. So how you did it? See, Alan, he's crafty. Okay, 6. 44.25 grams per mole. Okay. 7. Do I have an answer for 7? 704.5. So 704, 705, basically. That was a easy one if you utilized STP. So first step, you converted from grams to moles of ethane gas, ethane gas, and then converted from moles of ethane gas to moles of oxygen using your mole ratio, and then you could have gone straight from those moles of oxygen to the PV equals RT and solve for volume, or what? 22.4 liters per mole, because that's our cheap way when we have STP available. You can do one step versus plugging PV equals RT. Raise your hand if you did the one step 22.4. Raise your hand if you did PV equals RT. And that's okay. They're both totally acceptable, but I'm just trying to save your time. All right, 8. Yes, 224.2 liters for 8. And that's, some of us may not know that far. So let me pause for a moment. I'm going over this. Let's go over, I have 2 questions that I need to do with you because they're a bit more complex. So I want you to be comfortable doing the complex ones. So as we read through this, I want you guys to think about your process. This hopefully will take me 10 minutes or less, okay? So we have ammonium nitrate solid decomposing to dinitrogen monoxide and water, 0.03 mole sample of the ammonium nitrate. So write down your givens for yourself so we can set up this question together. 0.03 moles of ammonium nitrate is placed in a 1 liter evacuated flask. So we have N is equal to 0.03 moles of ammonium nitrate. We have volume of 1 liter flask. The ammonium nitrate decomposed completely according to the balanced chemical equation. That means it goes to completion. The total pressure, so the total pressure I'm guessing at the end, right? Because the first thing, does this cause any pressure? Why no? It's a solid, right? So that's not what it's referring to. The hard part is sometimes figuring out what it refers to. So the total pressure at the end, I'm going to put at end right here, is, oh, it doesn't tell us. Okay. That's what our question is. It's at 400 degrees Kelvin, and the R constant is, of course, given to us, but you know the R constant. So, if you're looking at the data, you're just looking at data, what equation stands out? P equals an RT, right? And so, in this case, this is a multiple choice question, so would you have a calculator? No. Let's try this. But before we can plug in, we don't have any gas. We haven't formed gas yet. We need to allow our reaction to occur. So we need to make a BDA chart. Okay, so now we're putting it, the ideas of BDA into a multiple choice question, which is doable. So I'm going to rewrite this because I don't have any space. Ammonium nitrate decomposes to dinitrogen monoxide and water. Ratio was 2. Okay. All right, so what do you know? What's your before? 0.03 moles of this, right? I may have lied on that last O. It was just 0.03. Okay. Okay, so before the reaction happens, there's no gas, so there's no pressure. You best not be plugging that 0.3 into your moles here. You need to get your gases first. And are both of these gases? Both of them said gaseous, right? Okay, gas and gas. So tell me how many moles I have at the end. What do I do? So you subtract all your reactant because it goes to completion. There should be 0 that's left. You implement your mole ratios here, but what are they? So plus what? 0.03 moles in a ratio of 1 to 1, right? So remember, your first one is according to the column you're under. The second one is your limiting reagent over here. And then you add again 0.03 in a ratio of 2 to 1 here. And so I'm setting up the BDA. You obviously could do this without the BDA, but of course this is great for organization. So in the end, you get 0.03 moles of this gas and 0.06 moles of this gas, totaling 0.09 moles of gas in general, because the identity of gas doesn't matter because it's all in the same container. This is N. And that's where people would mess up, right? And so if you're doing a multiple choice question, you should make sure you identify what the givens are so you can move on from there. If that's N, we have T and we have B and we have R. Let's go ahead and plug it into B because on our T, and let's try to do some mental math here. Solving for P, right? So nRT over B. Plug it in, units and all. Levi, start. 0.09, okay. 0.0821 atmospheres. Liters per mole. Okay, I think we all should get this tattooed later. We're going to put in this forever. Yeah.
It's the point of it to the direction, so would you use that instead?
Yes, but for a multiple choice question, it gives you specifics. I'm just such a habit there. So either way, you're doing mental math. It doesn't matter. T was what, 400 Kelvin? And B was 1 liter. Okay, mental math it up. I always try to assume if it's 0.8, 8%, 8% is about 10%. I can multiply by 0.1 by choosing, I can multiply by 0.08. So, tell me what you guys want to simplify first. Anybody? You guys are just mumbling. Okay, so this we're going to assume, just round it up to 0.1. 0.1 times 400 is what? 40. What's 40 times 0.09, which you can see is obviously about 0.1? About 4. Okay, but we've overestimated, right? So we've overestimated, so then our best answer choice, and did you guys, don't you write down what we just estimated? So this is about 0.1, we multiply by 400, that's 40. 40 times this, which is about 0.1, is 10% even less, so back decimal up 1, that's 4. 4 divided by 1 is 4, but we've overestimated on 2 accounts, right? So it's going to be our best option would be what? A, right. 3 atmospheres, not 4 atmospheres, or not whatever else you said. Okay, so you got this mental map in your pocket, right? Keep it. Don't lose that. All right, so last one that I wanted to do with you. Let me make sure it's not that one. It's one with methane. Okay. Methane. Did you say methane on here? Thank you. Thank you. Okay. So I want you guys to write down your givens for methane on this one. Number 3 right here. Write down your givens. I already have my shirt name. I'm going to do something. No one else was going to say. Alright, so you see this one a little bit more elevated because we're starting off with not just moles of everything, we're starting off with some different varieties of givens, but the varieties of givens can always be used using your same formula sets to find what you need, which is generally moles for a stoichiometry question. Sample of methane gas having a volume of blank. So as you're reading, you kind of skim everything, you see you have a reaction, right? What's our reaction? CH4, okay, yields. Okay, so it doesn't say incomplete combustion, so you're going with complete combustion by assumption. You balance it with a 2 and a 2. Yeah, okay. And then to help organize your information again, BDA is my preferred method because it helps keep you organized and you know what you're talking about, which is always the goal. Before the reaction, you have 2.80 liters of methane at 25 degrees Celsius in 1.65 atmospheres. And that's all information for methane. Mixed with a sample of 35 liters of oxygen at 31 degrees Celsius at 1.25 atmospheres. The mixture was ignited to form calcium or carbon dioxide and water. Calculate the volume of carbon dioxide formed at a pressure of 2.5 atmospheres and temperature of that. So where would that information go if you were trying to organize it in your BDA? That first right here in A. Would you put that right here in the carbon dioxide? Say again?
Yeah.
The after there, right? So the BDA, the after. So we're going to kind of make this big and organized. So after oxygen was calculate the volume of carbon dioxide at a pressure of 2.5 atmospheres and a temperature of 125 degrees Celsius. And then final B, calculate the total volume of the reaction after these at these same conditions after the reaction. So if part B is asking for total volume, where would we have total volume, or where would the pieces of total volume come from our BDA chart? So volume of CO2, volume of H2O, and then also maybe what? Maybe one of our gases over here that's also left over in excess, right? So do you see why the BDA table is actually kind of helpful? It's helping you organize that. Like each of your pieces, you know where they are, you know what they apply to, and you can add them up. So one of these is going to be in excess. We just don't know what that one is yet. Okay? So I want you guys to talk in your groups and see the best way. Johnny, scroll back up some. Like that. I want you to see the best way that you would approach this, given all that data. Take like 30 seconds to a minute. Give me a thumbs up if you think you have a course of action. Thumbs up if you think you have a course. Alright, so this would be a huge pre-response question that you could see something similar on your test or on AP Sam with multi-steps like this. I heard a lot of us say the same thing. What's the very first step? It has to be. We have to have moles using what? Ideal gas law. We have to, because there's not a consistent temperature. If there were a consistent temperature and a consistent pressure, we could actually use our liters, subtract liters, and find liters. And we would have our volumes at the end. But because our pressure is not consistent and because our temperature is not, we cannot do that. But know that for the future, if they are consistent, you could do liter ratios and call that a day because liters and moles are related through the 22.4 liters per mole. That's good if we have it, but we don't here. So I know that you can plug all this into the ideal gas law. I'm going to go ahead and tell you moles just for easy sake, okay? Cool. Don't hate me. I'm doing the math for you. Okay, so this is 0.188 moles, and you know that this came from the ideal gas law, utilizing, of course, temperature in Kelvin, not Celsius. That's our methane of oxygen is 1.7529 moles. Those are our two reactants before the reaction began. So 1.7529 moles. And I'm not rounding because that would cause double rounding error, and then I can have error in the end. So what do I do now? Who's my LR? Say again. Who's my LR? Say it loud and proud. You're probably right. Methane. 0.1 divided by 1 is 0.18 divided by 1 is 0.18. 1.75 divided by 2 is nothing close to that, right? Way excess, way LR. So methane is my LR, excess is in here, so this can be utilized at the very end for that total volume at the end. Okay, what do I do now? Subtract my LR, 0.188, subtract my LR, 0.188 in a ratio of 2 to 1, add my LR, and 0.188 in a ratio of, this is carbon dioxide by the way, 1 to 1, and then add my LR, 0.188 in a ratio of 2 to 1. Okay, so setting this up, and I saw that on your Unit 2s. We had some troubles with the BDA, to be honest, so I'm trying to keep reiterating that. So this one's 0 at the end. This is 1.7529 minus this is 1.375 moles of oxygen in excess. Okay, and then this is, of course, I'm just going to put N down here. So with 0 adding that would be N moles would be equal to 0.188 moles. And that's of carbon dioxide. And then this is times 2, so that's N is equal to 0.3776 moles. Okay, so I got moles everywhere. Did I go too fast? You guys okay? Okay. So after I get moles everywhere, were my two questions? I already have one of them labeled here, volume, right? So then what would you do here to find the volume? Ideal gas law for carbon dioxide. And then what would you do to find the total volume? Because this I don't know if you saw that, but it said the same conditions apply to the part B for total. So at this condition, pressure, temperature, or you know what, let's just make it easier. If all the stuff's at the same temperature, pressure, and you have the moles denoted for each of these at the end, do you have to do 3 separate PV exonerantes? No, for the total moles will be added together in total, and you can use that for your ideal gas law and plug it with your P and T and then your R. Don't do 3 separate ones. Does that make sense? Why are we doing that afterwards? Because that's for total, that's for V total, that's for volume total at the same conditions. So don't put more work on yourself. Yes.
So you don't just take the volume of the products, then you have to use the excess ones too?
Yes, because it said calculate the total volume after reaction at these same conditions. So after the reaction means after the reaction. If you have excess, you got to include it. And that's where people would mess up if they didn't have a BDA, most likely. Okay? So I walked through that. I want to let you guys kind of sit on that for a little while. But while you're sitting on that, look through the rest of your problem set. You guys have 20 minutes. Finish your gas Stoich. And then I'll put these up on the board if you want me to. If not, that's on you to do again. Okay, light homework. Get it done. It's only light because it's gas, but thanks. I like how people actually laugh at the jokes. I don't know if that was a true laugh, but it's close. Half time I'll say a joke in honors and they're just like, it's only funny if you know what we're talking about. Yeah.
What is the question on the temperature
From last night? Okay, give me a second. I'm going to pause this for Savannah.